Okay, lads, so welcome to Lecture 18, Week 12. We're looking at wood degradation. Um, we started our lecture off the same way we start all our lectures to date. We're talking about, we've had a quick list here of our recaps. So we've already spoken about a lot of topics, and we're in our final week now, so we're doing very well. Our MCQs are looking good. We've a couple of final submissions left to do. And don't be afraid that if you have any questions, just get on to myself, Edmund, or Maria, and we'll do everything we can to help you, okay? So we've looked at Ireland's history and wood, we've looked at silviculture, we've looked at growth of forests, we've looked at the scientific method, we looked at wood uses, norms and innovation, growth of wood, cellular structure of trees, angiosperms versus gymnosperms at a cellular level, drying of wood, data variance, understanding drying defects, ultrastructure of wood, chemical composition of wood, bonding, dimensional stabilizing and treatment, and we talked about the drying process. So we're moving on towards degradation, okay? So degradation is the process of something becoming worse or weaker, or being made worse or weaker, okay? So it's something happened to a material that's making it weak or making it worse, either aesthetically or physically as well. So there's a couple of important things we need to consider initially, okay? So we've got wood versus trees, okay? So wood is our finished material, so it's our focus on for this topic at the minute, degradation. We're talking about the wood itself, and then the tree is the mechanism of production, all right? So it's where we're getting the material from. We've got parasitic versus sapphoric, okay? So parasites live in or with another organism and depend upon them for life. Okay, so we're talking about ash dieback of Dutch elm as well. Sapphorites live off decaying dead material of other organisms. Okay, so you might be talking about the likes of fungal attack on an already dead piece of material. Okay, so global carbon flux. A carbon flux is the amount of carbon exchange between the Earth's carbon pools. So the oceans, the atmosphere, land, and living things. Okay, so wood decay contributes to a significant portion of 439 petagrams of carbon per year. Okay, so factors controlling degradation of wood. So degradation, we've got physical, chemical, and biological. Within our physical, we've got mechanical and environmental. Chemical, we've got inorganic and organic. Biological, we've got bacterial, fungal, insect, and animal attack. Okay, so I'm sure even just from hearing them keywords, you'll have an understanding of how maybe some of these might be affecting materials itself. So we're not talking about trees, we're talking about a piece of wood. That's the thing you need to remember. We're not talking about the mechanism in which the material is grown, we're talking about the end product, which is a piece of wood, and how these different types of degradation affect it. So physical degradation is often described as a mechanical degradation. So abrasion, friction, same action of sanding, use over time, grinding, you'll be talking about the manufacture of paper pulp, grinding logs against a stone wheel in the water. Okay, so basically with a physical or mechanical degradation, you're talking about something constantly making contact with a piece of material, and it'll eventually wear in or rub down the surface in such a way that it's going to leave its own mark, and it's going to leave its own background to what's actually happening to the piece of wood. Simple little things. If you think about a really old staircase you might have seen maybe in an old church or somewhere maybe in an old building, you'll often see where there's dips and hollows on the treads from where people are consistently walking up and down them steps in that area. Physical degradation, so we're talking about environmental factors now at the minute. So one of the things that we talk about is radiation. It affects us, UV rays affects us, it also affects our materials. We know it can affect plastics, but maybe some of us didn't realize it can affect timber as well. So radiation, right? So cellulose absorbs between 200 and 300 nm. So lignin is susceptible at 280 nm, so as a carbon hydrogen bond. Okay, so this breaks down the molecules into non-structural components through depolymerization. So it's effective to a depth of 75 micrometers. Happens at different rates. So softwoods we've got 6 millimeters per 100 years, and hardwoods we've got 3 millimeters per 100 years. So it's all to do with the effect of the sun and what it's going to do. It's actually going to start to delaminate or basically depolymerize the material, meaning that the surface of the material is going to start to become really weak and dry, and almost have a type of rot where it's going to start to fall apart. Okay, and then we've got, again, we're talking about environmental. So here we're talking about gases. So ozone O3, which is the lower layer, exposed to ozone can negatively impact growth of the trees. Okay, so enters the stomata and oxidizes tissues, causing burning during respiration. Okay, so SO2, so it's a negative effect on the ground of the trees, without any perceivable visual effect. So wind abrasion is another thing we find interesting, and we can see kind of in our own lives, and very easily see around the forest. So we've got wind abrasion, so we're talking about maybe sand and ice can also get caught into the air as it's flowing around the trees. But as well as that, just the trees getting hit with wind from a consistent direction each time, all year round. You'd often see there be less branches growing on that side of the tree, or all the branches would be leaning towards the opposite edge that's kind of sheltering from the wind slightly. And then we've got burning. So forest fires have a very high significance, and that was something that was very prominent last year, especially when we're talking about the likes of Australia and the likes of the environment that they have over there and the animals that are affected. So chemical degradation, we're talking about organic materials here, kind of. So ketoxin. So ketoxin is a chemical that'll start to dissolve the cellulose within the material, or it'll make the cellulose more dissolvable in water as well. And then acetate acid creates cellulose acetate, so it's starting to dissolve the acetate or the cellulose as well. Ethers, example, like a mentholated spirits or mentholated halide forms methyl cellulose, which is used in medicine. If you click onto that image, it should bring you to a link where you'll be able to see this in action. So chemical degradation, inorganic. So advantageous applications. So cellulose. What's affecting the cellulose here? So DMSO, dimethylated sulfide, dissolves cellulose extracts in it. Esters form with strong nitric and sulfuric acid. Accentations used to form rayons. So lignin. So what's affecting lignin that we often see? During the paper making process, there's depolymerization of lignin, that's done using the sulfide process. So pressure cookers with calcium biosulfate and sulfur dioxide is forced into the material and actually starts to remove the lignin within the material itself, creating a more bleached, organized and cleaner surface. And then the craft process, so it's cook the NaOH plus the Na2SH under pressure. Biological degradation, so we're starting to look at the likes of bacteria. So earliest colonizers of wet wood or moist wood is what bacteria would be. So found when fungi, insects and others cannot function. So resistant to preservatives. These types of wood degrading bacteria, so three types of wood degrading bacteria. We're talking about tunneling, erosion and then cavitation. So tunneling is lateral and longitudinal tunneling in the long axis of the wood grain. Cavitation is establishing a cavity in the S2 layer and secondary cell wall collapses. And then erosion, so gradually decrease cell wall thickness starting with the S3. So you can see here we're supposed to have a cell structure here between talking about S2s, S3s. We can see where cavitation is happening, we can see where erosion is happening, and then a little bit about tunneling as how it's passing around the cell. This here is a bacteria itself, and we can see the bacterial flagellum, which is basically the tail of the bacteria. We can see cell walls, and we can see all of the information within there. So fungi. So it's a complex structure, life cycle given opposite. So fungi requires temperatures of between 25 and 30 degrees and a pH level of between 5.5 and 5.5. Oxygen for metabolic process, anaerobic conditions okay for soft rot. Moisture content between 20 and 35%. Light not needed, so nutrients, cells and cell wall, carbohydrates, fats, and proteins. So all these different things that are needed. So if we can come up with some sort of a process to get rid of that moisture content that controls the fats and proteins, or controls the cell wall carbohydrates, the fungi will not be able to attack the material, which is something that's important. Okay, so within fungi itself, we've got spores, we've the hyphae, we've the mycelium, we've the fruit body, and we've spores. The damaging parts to this whole fungal process are the mycelium and the fruit pores or bodies. Degradation, so fungal groups. So we've got brown rot and white rot. Okay, so characteristics of these things, so damages the wood and affects the strength, differ in their preferred hosts, and then differ in their main food sources. We start talking about staining. We're talking about brown stain, sap stain, blue stain. We can see the no effect of wood strength when it comes to staining, but the actual rot itself can start to occur. Biological degradation. We're talking about brown rot. So there's two main species, Serpula lacrimas and then Conifera patina. Commonly associated with softwoods, preferentially attacks polysaccharides and leaves lignin. Wood goes a brown color. Cuboidal pattern on the surface of surface checks when dried. Hyphae penetrate cell walls transversely through pits and boreholes. So we're looking at the Serpula lacrimonis, dry rot fungus. It's a mycelium is able to penetrate mortar and cross sections. It appears white in moist conditions like cotton wool, grey white in dry conditions with small patches of lilac or yellow. Fruiting body is rust red. So we've got the brown rot then, and we're talking about the Conifera patina. Cellular fungus. It's a cellular fungus. Wood is very brittle and will kind of powder. It'll end up crumbling in your hands. Causes very rapid decay, which may be evident on the exterior of the wood. It likes moist conditions. Dampness and condensation help it to thrive. We've got white rot, so we're talking about Polypyrus versicolor. It attacks both cellulose and lignin. Wood appears bleached, not as damaging as brown rot. Incremental versus secession. Causes mild reduction in strength, and preferences is for hardwoods. Okay, so fungal damage comparison. So white rot versus brown rot. We're getting colors. We're getting explanation of what's going on. We can see what it's attacking. We can see how it's explained. And just by using them two little images, you should be able to almost look at a type of rot and tell me if it's white rot or brown rot based on your kind of assumptions from these. Now we're starting to look at biological degradation. So we're talking about insect attack here basically. Termites is something that we don't really have here in Ireland. We do have beetles that attack material. We've got woodworm. We've got powder post beetles. We all know what woodworm is. We can understand the problem with it, and it's boring materials. It's also creating holes for moisture to possibly travel through the material, and then allow for maybe even a fungal attack within them tunnels once the insects have left. So woodworm is an Anobium punctanum, or furniture beetle. It attacks hardwoods and softwoods. Powder post beetles are Luctidia. The Lictus beetle is between 2 and 7 millimeters in length. Attacks the sapwood of hardwoods. Small trachoid diameters make coniferous immune, and then holes are filled with finely powdered wood. So it does fill the holes as it's going through, but it's not with obviously materials that are any use to us. So it's a very short lecture that I'm sending you out today. It's our second last lecture, and I have that in mind due to the fact that your MCQ is on Friday, and that you have your CBA due this week or next week as well. So I don't want to put us under too much pressure. So there's a video here now where if you click onto that link, you're going to be able to go through the paper making process, and you're going to be able to develop your own understanding of degradation and why it becomes beneficial for us in the process of making paper and removing the lignin from that, which is something that is interesting, and it is actually seen in your everyday life, so there should be a direct connection between that and what you do in school as well.